So, having learned these autoencoders rather in a qualitative way, also seeing to the structure using these mappings etc. Let us deal with these denoising autoencoders. So, the idea is pretty straightforward. So, instead of having my original data vector, I look at a data vector which is corrupted with noise, and then I learn my mappings over this corrupted inputs, and this representation is hopefully robust to noise, and when I decode somehow I project, I remove this, I do this denoising in a way that I can come up with functions that can project the noisy point onto the manifold, learning manifold, and then get my clean input back. So, the only subtle difference between autoencoders and denoising autoencoders is that during the learning of the encoding we start with corrupted inputs rather than clean inputs, and the idea is hopefully this gives us a better or a robust mapping for our learning. Okay. So, let us write down the ideas here. So, you take a partially corrupted input during training to recover the original undistorted input data vector. Okay, and the hope is that we have an efficient representation that can robustly obtain the clean input from a corrupted representation. Right, I have an efficient representation that can robustly obtain the clean input from the corrupted representation. So, I have some assumptions towards this. So, we make some assumptions. The first assumption is higher level representations are robust and stable. The second is we extract features useful to represent the original data point density, right. We extract features that are useful to represent the original data point density, the data PDF. Okay. So, these assumptions are stated in the paper by Vincent et al. That appears within the journal on machine learning research, you can look into that original paper, or you can also see any refer to any good book on deep learning networks. Now, what is happening here, right? The first thing is stochastic corruption. So, you have a data vector x that gets transformed to x tilde, right, and that is some mapping, I call it SC, right, it is stochastic corruption. And what we do is we feed these corrupted versions, or we feed x tildes to the autoencoder for learning. So, there is a function which is the stochastically a corruption function which corrupts the data vectors, and I go from my space x to x tilde, and x tilde is a corrupted version, and the autoencoder instead of learning the clean inputs learns the corrupted version of the input, right. So, at this stage you will also question how do I measure loss, whether the loss is between the corrupted, because my autoencoder is learning the corrupted version. So, is the loss associated with respect to the fidelity between the corrupted version and the decoded version of the corrupted version, right. It is not the way it is set up. So, you look at the loss from the original input to what you decode from your corrupted version of the input. Okay. So, let me write the loss function. The loss is L x to x tilde hat, right. You may not like this tilde and hat that I have, but I will describe to you what it means. This is my original uncorrupted input, and this is my decoded output based on the encoded version of the corrupted input. This is a subtle detail. Right, I decode based on the encoded version of the corrupted input. That's the detail here. Okay. So, one can also have sparsity constraints. So, we can have sparsity constraints within the neural network. So, there could be more hidden units than the input, but very few of them can be active at a time. So, that can lead to something called dead neurons, right. You can have more hidden units than inputs, but very few of them could be active. So, therefore, one can bring in regulation constraints or regularization constraints into the functional that we are trying to optimize, so that we can weed out these dead neurons. Okay, that is an important detail. So, when you do actually when you solve problems or when you work on your research problems, you may want to consider these aspects, right. So, I have just discussed qualitatively here. You can set up the constraint optimization problem, and then you can actually solve towards building your solve for the parameters towards building your network. So, there is an interesting geometric interpretation to how these denoising autoencoders work. So, I have a manifold here, and I have data points just closely in the vicinity of this manifold. That is how I have learned. Points may lie there, but some points could be corrupted because of noise, and let me indicate this is QD of x tilde given x, right. That is the sort of mapping that I have, and this is within an epsilon ball around this data point, and indicative of stochastic corruption of the data vector x, which makes it lie away from the manifold script m. Now, we have this point here which is x tilde, which is our noise. I am bringing the same version here, right. I mean, just considering another x tilde here, let us say at different point, and this is also noisy, right. So, if you want, you can put some other index here indicating it is a different version. So, what we do is we project this back to the manifold to give us our point x back, which is approximately correct, and this is the denoising aspect of these autoencoders. And what you can think about it is, you basically have some other function which is g theta dash acting on these inputs, which is basically a corrupted version of the inputs, right. So, now this f theta here is sort of an interim representation for a coordinate system for points that lie on the manifold. It is an interim representation, or you can think about as interpreted. You can interpret as a coordinate system for points x on the manifold, and the dimension of the system, right, of this f theta is less than the dimension of x, right. That is a subtle detail. So, I have missed these underscores which we can put throughout. Okay. So, what is happening here is I have an interim representation or the latent representation over that can be interpreted as a coordinate system on this manifold for points on this manifold, and the dimension of this coordinate system is less than the dimension of the original input x. And now you have a mapping which is this g theta dash which projects your corrupted version back to the point which is closest to the manifold, and that is how your reconstruction happens. And you have the associated loss function, and then you have a measure of fidelity, and then therefore you can kind of optimize over all the parameters in your neural network. That is the composition of mappings at the input, composition of the mappings from the encode to the decode. You can optimize the parameters over these mappings, given that you know that you are optimizing the loss between the original input vector x and your x tilde hat. Okay. So, this completes a qualitative discussion on denoising autoencoders. So, more details as to why this works, theoretical analysis on guarantees of the working of this procedure, etc. I think this is sort of a research topic, and this is an active area of research work in the machine learning community. So, I would suggest that you read papers and other books or advanced books on this topic. So, from the course perspective, we shall stop here.